Good morning, all. Today we will see an introduction to magnetostatics. We have already studied electrostatics. Remember the basic problem in electrostatics. In electrostatics, we have certain charges Q1, Q2, Q3, Q4, etc., Qi, and we have a test charge capital Q, which is located at a distance Ri from the charge Qi, and we need to find out what is the force experienced by the capital Q, the test charge by the source charges. And for that purpose, we have used the principle of superposition. Also, we have evaluated the electric field at the point where capital Q is located. In electrostatics, we have taken the source charges Q1, Q2, Q3, etc., Qi are at rest, whereas the test charge capital Q, it may or may not be in motion. By superposition, we have evaluated the force experienced by the capital Q by the source charges. The expression is capital Q into E, where E is the electric field. What is the expression for the electric field? If we have several source charges Q1, Q2, Q3, etc., Qi, then the electric field due to these charges at some point where capital Q is located is given by 1 by 4 pi epsilon 0 sum over I equal to 1 to n Qi by Ri square into Ri cap, where Ri cap is the vector in the direction of Ri. Thus, in electrostatics, we have taken the source charges are at rest, whereas in magnetostatics, we are considering the forces between the charges and they are in motion. In magnetostatics, we are considering the forces between the charges which are in motion. We know that when the charges moves, it will constitute current. Now, to discuss the forces between the current carrying conductor, let us consider two cases. In the first figure, there are two conductors in which the currents are in the same direction, whereas in the second figure, the currents are in the opposite direction. Let the current in the first conductor be I1 and the second conductor be I2. In the first figure, the currents are in the same direction, and in the second figure, the currents are in the opposite direction. Now, is there exist any force between the two current carrying conductors? Yes. It is experimentally observed that in the first case, that is, when the currents in the conductors are in the same direction, they will attract. That is, the current in the same directions attract. Whereas in the second case, the currents are in the opposite direction, and it is observed that the currents in the opposite direction will repel. Why this happens? Why there is attraction and repulsion that is taking place, and that is depending upon the direction of the current in two parallel current carrying conductors. Now, the force responsible for attraction or repulsion between the conductors is not electrostatic in nature. It is not an electrostatic force. It is not electrostatic force because the electrostatic force existing between the charges which are at rest. Now, for the first time, we are encountering with a new kind of force that is called magnetic force. This is our first encounter with the magnetic force. In electrostatics, we have seen the stationary charges, they are producing electric field. In the same way, in the magnetostatics, we have moving charges, they will produce magnetic field, and this magnetic field is responsible for magnetic force. Just like the electric field is responsible for electric force, we can say the magnetic field is responsible for this magnetic force. Moving charge generates magnetic field. Now, how do you detect a magnetic field? The detection of the magnetic field is very easy. You can detect a magnetic field using a compass. Using a simple compass, you can detect a magnetic field. If you place a compass near a current carrying wire, you can detect the magnetic field. You can determine the direction of the magnetic field using a compass. Just put a compass near a current carrying wire. Now, when you put a compass near a current carrying wire, you will see an interesting thing. You will see that the magnetic field is not pointing away from the wire. The magnetic field is not going towards the wire, but instead you will see the magnetic field circles around the wire. This is the thing you will see when you put a compass near a current carrying wire. You will see the magnetic field circles around the wire. Now the direction of the magnetic field is given by the right hand rule. If you grab a wire, in your right hand, just hold a wire in your right hand with the thumb pointing the direction of the current. Grab a wire in the right hand with the thumb in the direction of the current. Then your finger will give the direction of the magnetic field.